this video, what I want to do is give you a quick little review of some trigonometry. So if you have a trigonometry test coming up, maybe tomorrow, this video is going to help you get you ready and prepared. Or maybe you're in calculus and you just need a quick refresher of some trigonometric concepts. Well, in this video, I'm going to cover multiple different concepts that you will absolutely need to know. So in the side of the description, I'll have everything timestamped. So therefore you can jump around as you kind of need certain topics, and you can always kind of refer back to, when they kind of are needed for a quick refresher, or to kind of like dive a little bit deeper into the examples. But this is typically a review I would give to my students before they would take a test, just to kind of go over all the concepts that we have learned in a particular chapter. And this one would be kind of like introduction to trigonometry. So check the description down below if you need something at a particular time. Otherwise, I'm just going to kind of go through each of these directions as well as the examples for each one. So the first one is going to be sketching an angle in standard form. So when we want to sketch an angle in standard form, you can see in this case we have a radian, okay? Now there's a couple different ways we can think about doing radians. And the way that I always like to kind of think about it or explain it with my students is just remember that we can use this kind of semicircle. So halfway around a circle is going to be pi, right? Or 4 pi over 4. Now my angle is only going to be 3 pi over those 4. So 1 pi, 2 pi over 3 pi over 4. So again, we always start at our standard. Our initial side is always the positive version of our x-axis. And then we're going to have our terminal side, which is going to go over right over here. So that is going to be an angle 3 pi over 4. Now, what about if we have a negative angle? So when we have a negative angle, we're just going to go in the opposite direction. We're now going to go in our clockwise direction. Now you can see my denominator, though, is at 6, right? Instead of a 4. So we're going to do the same idea here. Like we can create this as a semicircle, right? But now instead of breaking it up into 4 equal parts, I'm now going to go ahead and break this up into 6 equal parts. All right. So now that it's broken down into 6 equal parts, what I want you to see is like halfway around a circle would be 6 pi over 6, right? So we just need to go 1 extra pi over, or 1 extra pi over 6 over, and to get to our terminal side, which is now going to take me for an angle here that's going to be have a terminal side, that lies in the second quadrant. And then the last example here is we have degrees. Now degrees, we don't really need to worry about like this breaking up in little slices of pie and understanding stuff. You don't really need to do that anyways. Like the faster and better you get, you don't really need to do that at all. But when you're dealing with like degrees, we need to understand that what are our kind of key metrics, key points here for our rotations. So we know that like that's 90 degrees, 180, 270, 360, right? So all the way around circle is 360. And then to get to 420, I just need to go an extra 60 degrees, which I'll just estimate here to be right there. So this would be what we call an angle that has an extra revolution on it. Now, the next thing we want to do is find the positive find one positive, one negative coterminal angles. So the fastest, easy way to find coterminal angles is just speed add and subtract 2 pi. Now, it's important for you to understand, though, 2 pi can come in many different variations, right? Because I don't want to add and subtract a 2 pi to 5 pi over 4. What I want to do is I want to add and subtract a 2 pi that has the same denominator. So that is the same thing as plus or minus a 8 pi over 4, right? Wouldn't you agree that 8 pi over 4 is the same thing as a 2 pi? It is. So when I add and subtract a 2 pi over 4, right? So if I take let's actually write it out. So a 5 pi over 4 plus an 8 pi over 4, that's going to give me a 13 pi over 4. And when I take a 5 pi over 4 and minus a 8 pi over 4, not over 3, that is now going to give me a negative 3 pi over 4. So those are going to be my no two coterminal angles, actually my smallest 2 coterminal angles. All right, notice how one is positive as well as one is negative. So 13 pi over 4 and a negative 3 pi over 4. Now, what about one if you have something that is like 7 pi over 4? Or sorry, 7 pi over 3. I don't know why I'm changing up these 4s and 3s. Now, again, this can be another way that we can understand 2 pi. I don't want to add 2 pi to that, and I don't want to add an 8 pi over 4. Those don't have the same denominator as 7 pi over 3. But I could say plus or minus a 6 pi over 3. That is equal to a 2 pi. But here comes the problem. Because when I take a 7 pi over 3 and I subtract a 6 pi over 3, right? That just gives me a pi over 3. That's positive, right? So if I add a 6 pi over 3, that's going to also be positive. I need to find a positive as well as a negative coterminal angle. So what I need to do is I actually need to not add and subtract in this example. I need to actually subtract twice. So I'm going to take a pi over 3 and then minus another 6 pi over 3, which is now going to give me a negative 5 pi over 3. So the easiest way is typically to add and subtract 2 pi, but that's going to be when you have a positive or a negative angle within a revolution between 0 and 360 or 0 and 2 pi. If it's larger, then you're going to have to either add twice or subtract twice, or maybe even more than that to get to your coterminal angles to be within 0 to 2 pi. And what about if you have a negative angle? Well, again, like it's the same thing, guys. If you have something in degrees, just use degrees instead of radians. That's the same thing as plus or minus 360, right? So just take a negative 210, right? And then add a 360 degrees. So negative 210 plus 360, that is going to equal 150 degrees. And then take a negative 210 minus a 360 degrees, right? And that's going to be a negative 570 degrees. Okay, so it doesn't matter if it's in degrees or radians. Typically, you would want to add and subtract, but look out for angles when they are larger than, when they have an extra revolution, because that does kind of change the way that we approach things. The next one is going to be finding the reference angle. So the reference angle is what we call the acute positive angle between our terminal side and the x-axis. All right. So what I always like to tell students when we're trying to find the coterminal angle is there's a whole bunch of formulas. Sometimes you might have a textbook that tells you what to subtract, how to subtract. And to me, it's just uber confusing. What I would prefer that students understand for the reference angle is what quadrant this angle looks like. 185 degrees is just over 180, right? It's right there. The reference angle is just going to be this sliver. How far are you away from the x-axis? Right? Well, if I just went 180 degrees and I know that the like halfway around a circle is 180, I can say theta prime is equal to a 5 degrees. That is going to be my reference angle. Oops, where's this thing? In the next example here, oh, that's my favorite. There you go. I don't want that, whatever. Let's remove that from there. There you go. The negative 7 pi over 4, again, let's go ahead and graph it here. So if I wanted to go and graph this, now again, another way to look at this is you could say that 8 pi over 4 is all the way around circle, right? That's the same thing as 2 pi. So we're at 7 pi over 4, so we're 1 short. Again, we're also going to go in the negative direction. So it's going to look something like this. Okay, so that is going to be my angle, theta. The reference angle is, again, this positive acute angle between my initial side and the terminal side, which hopefully you recognize here. Theta prime is equal to just to a pi over 4. And that does not look like a pi over 4. There we go. Now it's fixed. All right. And then this example, we have a 19 pi over 6. Reference angle, again, it doesn't matter, guys. Notice here, again, this is one of those things where we have an extra revolution, right? 19 pi over 6 can be broken down into a 12 pi over 6 plus a 7 pi over 6. So if I wanted to graph this, 7 pi over 6, you know what? Let's not do a 7 pi over 6. Let's change this. Let's change this to a 17. 17 pi? Yeah, 17 pi over 6. So if I change this to a 17 pi over 6, then that is going to now be a 5 pi over 6. I thought I did that. Can't believe I didn't change that. Okay, so that's going to be a 5 pi over 6. So we have a revolution, 12 pi over 6, and then we have 5 pi over 6, which is right there. And again, that's like, it's going to be pi over 6 short, right? Because to get to 6 pi over 6, that would take us to that quadrant. So that is going to be my reference angle. So we can say theta prime is equal to a pi over a 6. All right, the next one is converting between radians and degrees. Now, I always like to tell students whenever you're doing a mathematical problem for trigonometry, you know, typically if the problem is in radians, do the problem in radians. If the problem's in degrees, then keep the problem in degrees. Sometimes we do need to convert between back and forth, like arc length and stuff like that. So it is important. And sometimes if you need to verify something, it is important. But I don't want you to convert, you know, back into degrees because you like degrees better than radians. Don't do that, okay? But it is important to understand how we do this. And basically to do this, all we're simply going to do is use our conversion ratio, which is either going to be a pi over 180 or 180 degrees over pi. And that all depends on what unit you're trying to go from in between. So if I'm trying to go from radians to degrees, I want to multiply by 180 degrees all over pi. The reason being is I want my pi's divide out, right? I want these pi's to divide out. And when these pi's divide out, now I'm just going to be left with a negative 11 pi. I'm sorry, no, the pi's divided out. So when I do this, these pi's are now going to divide out, And then 6 goes into 180 how many times? Well, that goes into 30 times, right? So therefore, 30 degrees. This is going to be negative 11 times a 30 degrees. And now you can say that answer, or at least my final answer now, is going to be a negative 330 degrees. Now, what about if I want to go from degrees to radians? Well, we're going to do the exact same idea, but we're just going to flip it. So now it's going to be pi over 180 degrees. All right. And pi over 180 degrees. So now I kind of have this fraction, right? I have 315 degrees, or not degrees, because the degrees are going to divide out. So let's actually divide those out. That's the whole purpose of this. Okay. So now I have 315 pi over 180. So how can I kind of divide things out? Well, I think the one thing that I recognize here is that this is 45 away from 360, right? And so therefore I want to see like, oh, 45, that looks like, does that go into 315 and 180? It does. And therefore now I can just reduce this or simplify this answer by dividing the top and the bottom by 45. And now what I'm going to get is going to be a 7 pi over a 4. Now, what about if you have something like this, a 5 pi over 7? In this case, you're going to need to use a calculator, okay? Because what the common thing that students have is they're like, oh, it's not in terms of radians, so it's not a radian. No, it doesn't matter. The main thing is, do you see a degree symbol? No. So if you do not have a degree symbol, in this case, then it's not degrees. It is radians. It's just not written in terms of pi. So what you're going to need to do in this case is you're going to need to multiply by 180 degrees all over pi, okay? And when you go ahead and do that, you're now going to get an answer of 326.58 degrees. Okay. And again, this is going to be rounded. You can round it in any way. Just want to kind of give you that example, but you're going to have to use your calculator in that example. So be careful with that. The next thing is find the point XY on the unit circle. So again, like you got to know the unit circle, or at least, the step method, at least the first quadrant, finding these coordinate points, I think is like extremely important. So, when you're going back to review for, trigonometry in the unit circle and evaluating, make sure you understand how to use the unit circle, how to find the coordinate points that are on that unit circle. I'm not a big proponent of memorizing the unit circle. I do kind of have my own process for being able to evaluate, which is basically like using reference angles and using the first quadrant. But it really is important. That's going to show up a lot of different ways, not just finding the points X, Y, which is, in my opinion, like fairly basic. So in this case, what we're going to do is kind of find our point. So 5 pi over 6, I think is important. Like here's the unit circle. Okay. So knowing where this angle is. So this angle, here, actually what I'll do here is I will copy and paste this for all three of these examples. Okay. So we'll just kind of do this rather quickly. So we have 5 pi over 6. So again, that's going to be almost there, right? So it's going to be there. Okay, 5 pi over 6. Now that is going to be directly across from this angle, which is going to have a reference angle of pi over 6, right? So what I always like to do is I always try to find where it's reflective in the first quadrant, which is this point right here. The only thing is this is in the second quadrant. That's why my x is now going to be negative. So this point is going to be negative square root of 3 over 2, comma 1/2. Actually, let's write it down below. Negative square root of 3 over 2, comma a 1/2. I'll go ahead and erase that. Okay. Over here, I have 7 pi over 3. So that's going to be all the way around the circle. And then 7 pi over 3 will be 6 pi over 3. And then I'm going to have an extra pi over 3, which is right here. Now, hopefully, the unit circle are the points in the unit circle. In the first quadrant, that's going to be a 1/2, comma a square root of 3 over 2. And then I have negative 7 pi over 4. So negative 7 pi over 4. So that's going to be, why am I doing negative 7 pi? That should be negative 5 pi over 4. What am I doing? Negative 5 pi over 4. So negative 5 pi over 4 is going to be from right here, which is going to be directly across from this negative pi over 4. You can hopefully see that reference angle. But again, it's in the second quadrant. So no, I don't want that. I should be a negative 3 pi over 4. What am I doing? Why did I messed this up? I'm sorry about that. Let me go and fix these points because this is not what I was trying to, this is not what I wanted to show. Okay, so negative 3 pi over 4. That's right. It should be right there. Okay. And what I want you to see, though, is how it's directly across from this point, right? in the first quadrant. Now, again, this is in the third quadrant, so everything is going to be negative, but that's going to be negative square root of 2 over 2, comma, a square root of 2 over 2. But again, I want you to see this reflection, this symmetry across the x-axis, or I'm sorry, across the origin in this example, because that plays into a point of how to evaluate the 6 trigonometric functions when you're given an angle, okay? So when we want to evaluate, what we need to understand is like what these points, like how can we use these angles to evaluate our trigonometric functions? Well, just remember sine of theta represents the y coordinate, sine of theta equals the y coordinate of any coordinate point on the unit circle. Cosine of theta represents the x coordinate, and tangent of theta equals the tangent of theta is y over x. Then we have the reciprocal functions. So we have the cosecant of theta, which is 1 over y, secant of theta, which is 1 over x, and then we have the cotangent of theta, which is an x over y. Okay, so how much room do we got? We got a lot of room? Okay, guess we got a decent amount of room here that we'll get into. Okay, so let's go ahead and evaluate all 6 of these. So I think the main thing that we want to do for each of these points before we go and evaluate is figure out the coordinate point, right? So hopefully you recognize 7 pi over 6. That is going to be in the third quadrant, all right? So everything's going to be negative and has a reference angle of pi over 6. So if I go into the unit circle, I can see that this coordinate point is going to be negative square root of 3 over 2, comma, a negative 1/2. Okay, so again, I'm doing things rather quickly. Hopefully you can kind of follow along. So if I want to find the sine of this, that's going to represent the y coordinate. So sine, I'll just do sine of t because we already know t right there. So sine of t in this case is going to be a negative 1/2. Cosine of t is going to equal to a negative square root of 3 over 2. And the tangent of t, now this one's going to be a little bit more work here, right? That's going to be the y over the x. So that's a negative 1/2 divided by negative square root of 3 over 2. The negatives go to positive, right? And now I'm going to be left with a 1. The 2's divide out. So I'm left with a 1 over negative square root of 3 over 2. So 1 over a square, oops, let's put an equal sign here. So therefore, this is going to be a 1 over a square root of 3, which you can rationalize the denominator by multiplying a square root of 3 on the top and bottom. And that's going to give you a square root of 3 over 3. Again, that's a positive. Now let's go through the reciprocal functions. So the cosecant of t. So remember the cosecant of t is just going to be reciprocal, right? So that's going to be a negative 2. The secant of t. Secant of t is going to be reciprocal over here. So that one's going to be a 2 over negative square root of 3, which again, rationalize the denominator. So multiply by a square root of 3 on the top and bottom. That's going to be a 2. So it's still a negative square root of 3 over 2 over a 3. And then we have the cotangent of t. So cotangent t is basically this exact same one, just flipped, right? So now the 2's again will divide out, and that's just going to be left with a square root of 3. Now, I don't want to write out all those again, so I am going to copy and paste this. Hopefully I can do this perfectly. I think I did. And let's do it all over again. Haha. Oh, I did miss up one. That's okay. We can go and add a nice little line here. There you go. All right, so put a line there. All right, so now let's go and do this point. Now this point, I'll do a different label here. So negative 5 pi over 4. So negative 5 pi over 4 here is, that's going to be in the second quadrant. I think that's maybe where I asked that. So that's going to be in the second quadrant. The reference angle is going to be pi over 4. So that angle is square root of 2 over 2, comma square root of 2 over 2. But since it's in the second quadrant, my x is negative. So that's a negative square root of 3. I'm sorry, negative square root of 2 over 2, comma a square root of 2 over 2. Okay, so the sine represents the y coordinate, square root of 2 over 2. Cosine, x coordinate, negative square root of 2 over 2. Tangent, which is y over x. Well, guys, these are the exact same thing, right? So anything divided by itself is just going to equal 1. In this case, one of them is negative, so it's negative 1. Cosecant is going to be 1 over y. So let's go and do that. So that's a 1 over square root of 2 over 2. Again, multiply by your reciprocals here, or multiply over here. You're basically going to have a 2 over square root of 2. You rationalize the denominator on the top and on the bottom, and you should be left with a, let's actually rewrite this out. Actually, I forgot this one. So if you multiply, so you're going to have a 2 over a square root of 2. Rationalize the denominator, right? And you're just going to be left with a square root of 2. Yeah, okay, that's what I thought. So rationalize the denominator, and that's going to leave you with the square root of 2. Now, the cool thing about pi over 4 is whatever you get for cosecant, you're going to get for secant, right? They're basically the exact same answers. Except notice, obviously, cosecant is negative, right? So that's a negative square root of 2. And then cotangent is going to be x over y, which is, again, same thing over the same thing. So that's going to be a -1. And then let's go ahead and play this game one more time and evaluate now for this angle at 3 pi over 2. Now this angle is interesting because we need to, this angle is not this is not a coordinate point on within the unit circle. This is actually on an axis. And this coordinate point here is 3 pi over 2. That's going to be at 0, -1. Okay, so kind of a little interesting here. So my sine in this example is going to be my y coordinate, which is -1. Cosine, x coordinate, which is 0. Tangent, which is y over x. So that's going to be -1 over 0, which, ladies and gentlemen, you can't divide by 0. So that is undefined. Cosecant, though, is 0 over -1. So that's going to be 0. Secant is 1 over -1, which is just -1. But cotangent, guys, I'm sorry, secant. Did that wrong. Secant, sorry. Let me slow down here. Tangent was undefined. Good. Cosecant is 0 over -1, which is 1. Oh, no, I got those wrong. Cosecant is 1 over y, right? So that's 1 over -1, which is -1. Secant is 1 over x, which is 1 over 0, which is also undefined. And cotangent is x over y, which is 0 over -1, which is equal to a 0. Okay, so that was going through all of them. Now, let's go ahead and just evaluate these basically just where they're at. So I'm going to even do these even a little bit quicker here just to be able to find my coordinate points. So the sine of 5 pi over 4, I'll kind of talk my way through it. That is 5 pi over 4. That is going to be in the third quadrant. That means my y coordinate is negative. The coordinate point here is going to be a square root of 2 over 2. So therefore, that's going to be a negative square root of 2 over 2. Cosine of -pi over pi halves. Actually, let's sketch the angle here. What I'll do is I'll sketch the angle so you can just kind of see how I'm getting it, right? So there's the point right there, and it's going to be a negative square root of 2 over 2, comma, negative square root of 2 over 2. There you go. So the answer, whatever. So the answer here is a negative square root of 2 over 2. Over here, my answer, negative pi halves, is right there. The x coordinate in that case is going to be a 0. 4 pi over 3. So 4 pi over 3 is down all the way down here. Now this one, sometimes for tangent, I do like to write the x and y. So pi over 3 has the reference angle of pi over 3. So that's going to be a 1/2, comma, a square root of 3 over 2. But again, remember, it's in the third quadrant, right? So that's a negative and a negative. So now I have the y coordinate over the x coordinate. Well, the negatives and the 2's are just going to divide out. So that's going to leave me with a square root of 3. Cosecant of 3 pi. Let's see, where's 3 pi? So here's 2 pi, 3 pi, which is going to be -1, 0. Cosecant is going to be 1 over y, which is going to be undefined. Secant of 5 pi over 6. 5 pi over 6 is right here. Let's see, what is that coordinate point? I think that coordinate point is going to be a square root of 3 over 2, comma, 1/2, but it's in the second quadrant, so that's a negative, right? So the cosecant is going to be 1 over a negative square root of 3 over 2. So -1 over square root of 3 over 2. So therefore, remember, rationalize the denominator, multiply by the reciprocal on top and bottom. That's going to be -2 square root of 3 over 3, right? So multiply, yes, boom. Okay. And then cotangent of pi over 3. So pi over 3 is right there. So again, that coordinate point here is going to be a 1/2, comma, a square root of 3 over 2. And cotangent is going to be x over y, right? So that's going to be a 1/2 over a square root of 3 over 2. And that's going to equal to a square root of 3 over 3. And that's going to remain positive because, again, it's in the first quadrant. So positive, negative, undefined. That should be positive because those are both negative. Okay, I think I got everything right. Just want to make sure I wasn't getting my mistakes. Now this one is evaluate the 6 trigonometric functions. So these are not on the unit circle. So we have to do something different. We actually have to go back to old school on how to evaluate. So if I want to evaluate the 6 trigonometric functions, and if I'm giving cosine of theta is equal to 1/3, what I need to do is go back to what we originally did, create a triangle. So that's exactly what I'm going to do here. Say, all right, here's theta. Cosine, remember, is adjacent over hypotenuse. Now I can use the Pythagorean theorem here, right, to go ahead and find this missing side. So remember, 1 squared, plus x squared is equal to 3 squared, right? And when I do that, I'm going to get the square root of 8, which can be simplified here to a 2 square root of 2. So now I have all sides of the triangle. Now again, remember my adjacent side is between my angle and my 90 degree. 3 is always the hypotenuse, which is always directly across from 90 degree angle. And then opposite of your angle, right, is called the opposite side. So now we just need to remember our trigonometric functions here though. And this one sometimes students do forget. So just remember a sine of an angle is going to be the opposite over hypotenuse. Cosine of an angle is equal to the adjacent over hypotenuse. I don't know why I'm writing it like this. Yeah, and then the tangent of theta is equal to hypotenuse over, opposite over hypotenuse. Now, I don't have room, opposite over adjacent. What am I doing? Jeez, man. Adjacent. Now, I don't have room to do the reciprocal functions, but hopefully you recognize the reciprocal is just going to be those flipped, right? So here's our theta. So in this case, if I want to find the sine of theta, that's going to be opposite over hypotenuse. So that's going to be a 2 square root of 2 over 3. Cosine of theta, we already have. That was given to us. That's 1 over 3. And tangent of theta is going to be opposite over adjacent, right? So that's going to be a 2 square root of 2 over a 1, which is just 2 square root of 2. Now, the cool thing is for the reciprocal functions is just flip them, right? So if I want to find the cosecant of theta, what I'm simply going to do is just flip this 3 over a 2 radical 2. Now you can rationalize the denominator here. When you do that, you get a 3 radical 2. That'd be radical 2 times radical 2, 2. So that'd be over 4. For the secant of theta, you just do a 3 over 1. And for the cotangent of theta, cotangent of theta, I would just have a 1 over 2 square root of 2, which again, you can rationalize the denominator, multiply by square root of 2 on top and the bottom. And that'd be a square root of 2 over 4. Okay. Now, let's go ahead and copy all these again because I don't want to rewrite them. And let's do it from this case. Now, for this next problem, things do get a little bit more tricky because you're like, Mr. McLogan, I don't have a angle that's on the unit circle. All I'm given is a point. How am I supposed to do this with just given a point? Well, remember, this point is not on the unit circle, so don't try to do that. Do not do that. That's the most common mistake that happens here. Do not do that. What you are going to have to do is plot this point. So we have 1, 2, 3, 4, 5, 1, 2. So we have 5, negative 2. Now what's cool about this is we can create a triangle here. 5, negative 2, right? And then from there, we can also go ahead and find the hypotenuse, right? So we have a 5 squared plus a negative 2 squared equals, well, that's going to be what, a 29? Let's just call this an x squared, right? So that's going to be a square root of 29 is going to be your hypotenuse. Okay, so square root of 29 is going to be your hypotenuse. Let me actually rewrite that a little bit more, a little bit better. So what you do is basically you plot the point on the plot the point on the quadrant system, and then you now use Pythagorean theorem to find the hypotenuse. So now let's go and evaluate. So sine, remember, is opposite over hypotenuse. So here, another thing I want to mention is your angle is going to be what we call our central angle. So it's always going to be at this point. So make sure you draw your angle. Always make sure you have a side along the x or always make sure you have your side along the x-axis, okay? Always have a side along the x-axis. We're not doing this across the y because we have to use our theta. We have to be able to use our theta, which is going to be a central angle in this way. So always make sure you have a side along the x-axis. Very important. So sine of theta is opposite over hypotenuse. So therefore, that's going to be a negative 2 over square root of 29, which you can rewrite as a negative 2 square root of 29 over 29. Cosine is going to be adjacent over hypotenuse. So that's going to be 5 over square root of 29, which again, that's going to be a 5 square root of 29 over 29. Tangent is opposite over adjacent. So that's going to be a negative 2/5. So cosecant, the cool thing here is like, now I can just do the reciprocal, like just flip them, right? So I can do a square root of 29 over a negative 2. Much better. Secant, I can just do a square root of 29 over a 5. Much better. for cosecant. And then I can do the cotangent, which is just for the cotangent, I can just do a 5 over a -2. Much better. All right, let's do one more. Now, in this problem, though, it even gets even a little bit trickier, okay? And the reason why this problem gets a little bit trickier is because now we have a triangle, but in addition to having a triangle, we have a constraint. Oh, what's up with these constraints? Okay, so we have tangent of theta equals 1 pi over 3, but it says secant is less than 0. So we got to understand, when is secant less than 0? Remember, secant represents like the 1 over x, right? And you could think about that as like, let's think about the coordinate point, 1 over x. Well, when is x negative? X is negative in the second and the third quadrant. Now, when is tangent positive? Tangent is positive, okay, in the first and the tangent is positive, which 1 over 3 is positive. Tangent is positive in the first and the third quadrant. So secant is negative in the second and the third. Second and third. Tangent, let's maybe draw this up. Come on. All right. So secant is negative in the second and the third quadrant, right? Whenever x, secant's 1 over x. So whenever x is negative, that's second, third quadrant, it's negative. Tangent, though, is positive in the first and the third quadrant. So what is the only triangle here that works? It's going to be one in the third quadrant, right? So then what I'm going to do here is I'm going to draw my triangle. Let's draw it maybe bigger. In the third quadrant. Now it said tangent of theta, which is 1 over 3. Now notice again how my triangle here has that x-axis, right? My 90 degrees right there. So there's going to be my theta. And it's what? Opposite over hypotenuse. So that's 1 over 3. Add those together. Was it 1 over 3? Yeah. No, I don't want to do 1 over 3. Let's do, I don't want to do that. Let's do 4 over 3. There you go. 4 over 3. The reason why I want to do 4 over 3, because now I recognize this is a Pythagorean triple. Let's make our life a little bit easier here. I already did radicals. And that's going to be a 5. All right, so sine is going to be opposite over hypotenuse, 4/5. Cosine is adjacent over hypotenuse, 3/5. Tangent, opposite over adjacent, which we already had, which is 4/3. Cosecant is just a reciprocal of sine, so that's 5/4. Secant, reciprocal of cosine, 5/3. And cotangent, which is reciprocal of tangent, is going to be a 3/4. Voila. All right, now let's get into some trigonometric functions like identifying the period, the amplitude, the phase shifts, the domain, the range, and sketch one period of the function. Crap, I didn't know I had to sketch. All right, let's get into the sketching. So first thing we want to do is understand the period. So remember, for sine and cosine, the period is going to be 2 pi divided by b. Okay, so my b in this case is going to be what is my coefficient of my x. So my period is going to equal to a 2 pi divided by 3. Done. My domain is going to be all real numbers. So my domain here is going to be all real numbers because there's no restrictions here. Now my range is going to be how high and low the graph goes. Now again, that's going to include the amplitude as well as any shifts up or down. So the typical graph of a sine graph goes from -1 to 1. But now this graph is being shifted down 2 units, right? So instead of it going down as low as -1, it's now going down 2 more units, which is going to be from -3. And if the highest point was at 1, but went down 2 units, now that's only going to go to a -1. So my range is going to be from -3 to -1. The other thing I like to do is when I'm trying to go ahead and sketch a graph is I like to find the x scale. So if I want to try this, what I want to do is find the x scale. And to take the x scale, all you're simply going to do is take the period and divide it by 4. So what I'll do is I'll take a 2 pi over 3 and I'll divide that by 4. So in dividing by that 4, I'm going to get a pi over 6. Okay, so that's technically a 2 pi over 12, which just reduced to a pi over 6. The reason why that's important is because that kind of tells me all the important points of this graph. Okay, so what I can do is like kind of say, all right, I have a pi over 6. This would be 2 pi over 6, which would be a pi over 3. Then I have a 3 pi over 6, which is pi halves. And then I have a 4 pi over 6, which is a 2 pi over 3. Okay, so there's 4 important points. Here, 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 and here. Actually not, it just says sketch graph, right? Yeah. Well, whatever. But again, remember, this is not your x-axis, is it? Right? Technically, your x-axis is up here. This is like at what, -3, -1? -1, 2, 3, yeah. So there's kind of like my x-axis. So my graph kind of looks something like this. So sine goes up to negative. Oh, no, wait, crap. I made a mistake there. That should be at like -2. Okay. So that would be as high as -1. Yeah. That would go -1, -2, and then -3. There you go. So what you do here is you go up to this point, then this is going to be an intercept. Okay, and then it goes down to your lowest point, which is -3, and then back up, right? And that's gonna be like roughly 1 period of your sine graph. And again, just remember the amplitude still has an amplitude of 1, right? Which is the half distance from the maximum, but this graph was shifted down 2 units. Right, okay. So the next one, period. Now in this case, this is nice because my period is still going to be 2 pi. So period is equal to a 2 pi divided by b, which in this case is a 1, right? So 2 pi divided by 1 is just 2 pi. Period is going to be 2 pi. Got that. And then domain and the range. The domain here is, again, all real numbers. Domain and range for sine and cosine is always going to be all real numbers. The range, though, now in this case, we don't have any shifting up or down, right? But now what we do is we have a stretch. We have a vertical stretch of our graph. So now my graph does not have a, now the graph has a range here from down has been stretched now to -4 up to +4. So now my range here is going to be -4 to +4. Okay. Now my x scale is still going to be like the general parent function, which is going to be every pi over 4, right? Take your period divided by 4. So 2 pi divided by 4. 2 pi, sorry, it's pi halves. No, not pi halves. Yeah, 2 pi divided by 4 is going to be at pi. Yeah, it is at pi halves. Idiot. Jeez. It's going to be every pi halves. But there's something that happens. My graph has been shifted pi halves to the left. Okay, so we're going to go through our shift here. So my x scale is every pi halves, but now this plus pi halves means it's shifting pi halves to the left. So I'm negative pi halves, 0, pi halves, and then pi halves plus another pi halves, which is going to be at pi. Okay, now cosine looks a little bit different. Oh, and this goes 1, 2, 3, 4, 1, 2, 3, 4. Okay, so now the graph goes up 4, down 4. Now cosine looks a little bit different than sine, right? The starting point is up here, then it's going to cross, go down here, and go up to there. So the graph is going to look something like this. And again, guys, this is just 1 period. You can obviously repeat this graph, and that's a really horrible graph, but hopefully you kind of get the idea here. Now, tangent is completely different from sine and cosine. The graphs don't look anything alike. The period is now going to be pi divided by b. So in this case, what I have here is a pi divided by pi halves. Well, when you multiply by the reciprocal here, you're going to get a 2. Okay. So period is equal to 2. There is no amplitude. The range in this case now is all real numbers. But for the domain, it kind of gets a little tricky. And so what I always like to tell students for the domain here is you take whatever's inside your function. So in this case, so here's my domain. You're going to take pi x over 2, and you're going to set that equal to the asymptote equation, because the domain is going to be, your function is going to be defined for all values except for where the asymptotes occur. So you have to know when the asymptotes occur for tangent. And the asymptotes occur for tangent is going to be every pi halves plus pi n. Okay. So now what we need to do is just basically multiply by a, now we simply need to do is just multiply by a 2 over pi. So when I multiply everything by 2 over pi, what I'm now going to get is x is equal to, let's see here, 2 over pi. So that's going to be a 1 plus a 2n. So it's going to be 1 plus 2n is going to be your function. So my domain here is going to be all real numbers such that x cannot equal a 1 plus a 2n. So it'll be like 1, 3, 5, right? So every 2n from on there. All right, so how is this going to look on my graph? Well, kind of a little interesting here. So if I need to graph a tangent here, what I need to understand here is I need to know what the graph looks like. Tangent, like, is that little kind of S curve. what am I doing here? Okay. I need to know my asymptotes are going to occur at 1. Now you can add a 2 pi, or 2, right? Or you can subtract 2. If you subtract 2, that'd take you also to a -1. And now we can just kind of sketch our graph here to look something like that. So that's going to be from 1 to a -1. I don't know why I did a cotangent. Let's swap these. Because now that I figure you might as well do these two like next to each other because they're much more similar. Okay. All right, cotangent. Now in this case, notice we have this, in this case, we have this little transformation here. So what we want to do in this case is going to be flip that around and factor it out. So when I factor out the negative, now I'm getting left with a pi halves, positive pi halves. Come on, what am I doing? Factor out the negative x, I'm be left with an x minus a pi halves. Okay. Did it say phase shift then sketch? Oh, phase shift and domain. So here is going to be, sorry, I did forget to add in. So this is going to be down 2 units. Here is going to be a shape shift pi halves left. Here's no phase shift. Here we have a phase shift. Now again, here's the important thing. So not only are we going to now reflect the x-axis, no, the y-axis. That's a negative inside, so that's going to reflect the y-axis. But now we're also going to have to shift this pi halves to the right. Okay. So let's go and talk about the domain. Domain is going to be our pi divided by b, which b in this case is going to be a 1, right? So therefore my period is just going to equal to, period is just going to equal to a pi. Let's see here. Period is going to equal to pi. My range is going to be, again, all real numbers. Now my domain, just like we did for over here, domain, what we're simply going to do is I'm going to set this equal to negative x minus pi halves. Now what I'm going to do though is I'm set whatever necessary function equal to the asymptote equation. Now what's the asymptote equation for domain? I'm sorry, for a cotangent. For cotangent, that's going to be a pi n. Okay, so don't really need to be, like, n represents any integer. So when you divide by negative, it's not really change anything. So now I'm just going to have x is equal to a pi halves plus a pi n. Okay, so my domain is going to be all real numbers such that x cannot equal a pi halves plus a pi n, which is actually the original domain of tangent. Kind of interesting here. So let's see what this graph is going to look like. Basically, I'm going to take the cotangent graph. I'm going to reflect it about the y-axis. Okay, so let me show you how this would kind of work. Here's the cotangent graph. Cotangent graph looks something like this, right? There's pi. Now, if I take this graph and I reflect it about the x-axis, that's now going to look like this. I wanted this. Okay, now again, this intercept here is at pi halves. Here is at negative pi halves. Okay, now let's take this graph and shift it over pi halves to the right. And guess what I'm now going to get? I'm now going to actually get the tangent graph, which is kind of cool. So this graph here is going to be a negative pi halves. And this asymptote here is going to be at pi halves, which matches my domain anyways, right? And also matches, you can see the reflection. So we reflected it and then we shifted it. So kind of like a two-part there. Okay, so when you're dealing with the reciprocal functions, these can be kind of tricky. So what I always like to do with my students is I always like to tell them to, hey, why don't we just go ahead and graph the reciprocal function of these functions and then graph the sine and cosine tangent. So y is equal to a negative sine of x plus a pi halves. Like, what would that graph look like? Okay. Now, again, let's go and figure out the information. Let's go and figure out the information here real quick. Actually, let's let's go and graph it and then we'll figure out that information. So if I was going to go and graph this, Notice this is the sine graph being shifted pi halves to the right. Okay, so here's pi halves. The x scale is still every pi over 4, so pi halves, pi, 3 pi over 2, 2 pi, and then there'd be a 3 pi, and then be a 2 pi, and then be a 5 pi over 2. Okay. And then it's being reflected, though, about the x-axis, because now the negative is on the outside instead of on the inside. So therefore, here's a -1, here's a +1. So now the graph looks like this. Go up to there, up to there. Now, again, that is the sine graph. That is not the reciprocal graph. When I'm graph this reciprocal function, I'm using these asymptotes. Like wherever there's an x-intercept, that's where the asymptotes are. And then this graph is going to go in this reciprocal format here, like here, and right there. So you're just going, again, remember your graph is approaching these asymptotes from the left and from the right. Okay. Now, how do we figure out all the information? Okay, so let's go ahead and write it down. My period is, again, going to be, there's no period. I'm sorry, there's no period in this case. We have a reflect the x-axis. We have a shift, a phase shift, pi halves to the left. And then my range, so my domain range is actually a little bit difficult. So my domain, again, what you're going to do is set your domain. So your x equals pi halves. So x plus pi halves, whatever's inside your function, you're going to set that equal to where your function is going to have a where your function is going to have asymptotes. So if you think about cosecant, cosecant is going to be undefined at pi halves plus pi n. If you kind of go to the unit circle, if you think at pi halves, that's when y is equal to 0. So that's going to equal to a pi halves plus a pi n. Okay, so if I go ahead and solve for x, I get x is equal to, so my domain is going to be a pi n. So my domain is going to be all real numbers such that x cannot equal a pi n. And you can see that works, right? If you go back to my graph, look, it's at pi, 2 pi, right? And that's where those asymptotes are. Now, in terms of the range, you can see that the graph is defined for everything below -1 and everything above 1. But anything in between -1 and 1, it's not defined. So my domain in this case, or I'm sorry, my range is going to be from -infinity to -1, union 1 to infinity. Okay, so it's going to be from those 2 points. All right, let's go and do this one. So in this graph, we have y equals 2. This would be cosine of x minus a pi. Okay, so let's go and see what that graph would look like. If I was going to graph that, I'm now going to have a vertical stretch, right? So that's going to be going up to 2 and down to 2. And then notice that this is actually shifting the graph 2 units to the right. So here we're going to be at pi. So the graph is kind of like all the way over there. Okay, so now the graph is going to look something like that. Oh, it still has a, let's just kind of do, so if you're starting at pi, it still has a, an x scale because the period is still 2 pi, right? So period is equal to 2 pi. This one still has a period equal to 2 pi, right? So therefore the x scale is going to be pi halves. So if this is a 4 pi over 4, then you could do a 5 pi over 4. Then you could do a 6 pi over 4. Running out of space. 1, 2, 3. Okay. But the main important thing is it's going up to 2 and down to -2. You know, let me finish. I want to fix this in there. Gotta fit it. Okay, so that'd be a 6 pi over 4. And then you could do a 7 pi over 4. No, wait a minute. Yeah, pi over to the right. Yep, and then we do a, I'm an idiot. I'm going by pi over 4. Why am I doing pi over 4? Sorry, guys. That'd be a pi halves. So the next one would be a, that's a pi. So then the next one is going to be a 3 pi over 2, a 2 pi or a 4 pi over 2. And then this would be a 5 pi over 2. And then this would be a 6 pi. Having some trouble counting. Sorry about that. All right, so that is a 6 pi. Now again, we go ahead and graph this. Okay, but again, it's important, ladies and gentlemen, to understand that that is not what the graph looks like. Okay, that is not our graph for secant. Our graph for secant has asymptotes right here. Asymptotes right here. And it's going to be approaching those asymptotes from these 2 points. Okay, notice the low points. Notice the low point -2 and +2. Okay, notice those points. It's very important. So what did this graph do? What did we have? So the only transformation we had in this one was just a shift right pi. So we could say right pi. My domain, again, what you're going to do is take whatever's inside your function. So my domain is going to be x minus pi, and you're going to set it to your when your function is undefined for secant. And secant's going to undefined. If you think of the unit circle, 1/x, right, is when is cosine, is secant. So when is x going to be 0? Well, that's going to be at every pi n. So x minus pi is equal to a pi n. So therefore, my domain is going to be all real numbers such that x cannot equal a pi plus a pi n. And my range is basically, again, saying how low does the graph go to how high does it go? Notice nothing's happening between -2 and 2. So my range here is going to be, why I'm using brackets here, is going to be a -infinity to -2 union +2 to infinity. Voila. Okay, now let's go ahead and work on the inverse. So the main thing to understand about the inverse is like when I'm evaluating a function, I have to say tangent of theta, that is equal to y/x, right? So when I say like tangent inverse of 1, basically what I'm trying to do is I'm trying to find what the angle is, right? So basically what this is saying is tangent of what angle is equal to a 1, right? So when you're trying to understand this, you're saying theta is equal to a tangent inverse of 1. So what angle is going to produce a 1 when I take the tangent of it? Now, it's also important to understand our restrictions because we have restrictions for the inverse tan, inverse cosine, and inverse cosecant. So the tangent is going to be restricted to the first and the fourth quadrant. Cosine is restricted to the first and the second quadrant. And sine is restricted. Sine is going to be restricted between the first and the fourth quadrant as well. So in this case, excuse me, when I have the, okay, so if I want to say the tangent of theta is equal to 1, basically what I'm saying is what angle is going to produce that? Well, this angle here is going to be a pi/4. And why? Because what's pi/4 here, guys, is that square root of 2 over 2, comma, square root of 2 over 2, right? And that y/x is equal to 1, which is going to give me my +1. I can't use this angle over here because you can see that's not within the restriction, right? I can't use 3 pi/4. And the reason why is don't both of these angles, when you take y/x, let's go and look at this one, negative square root of 2 over 2, comma, negative square root of 2 over 2. Don't both of these angles, y/x equal 1? Yes. But what's the difference between this one and this one? This one is within my restriction. This one is not. So that's why the answer, the final answer is there's only one answer. And you can always verify this. When you use your calculator, like these are called inverse functions. Okay, so there's only one answer. That's why we have these restrictions, because if we didn't have these restrictions, there'd be infinite many answers. Okay, so we only use these restrictions to be able to get our one answer. And in this case, my final answer here, theta, is going to equal a pi/4. Now, what about cosine is equal to -1/2? When is the x coordinate equal to -1/2, right? You can think about cosine represents the x coordinate on the unit circle. So cosine is equal to -1/2 over here. Cosine is equal to -1/2 here. And if you were to continue this unit circle, it'd be down here, right? But again, do I care about this one? No, right? That's not within the restriction, right? So we don't care about that. Actually, I can even write that there. So then what about this one? What is this coordinate point? -1/2, comma, square root of 3 over 2, right? What angle produces that? The angle that produces that for this angle, theta, is going to equal a what? 2 pi over 3. And voila. What about this example? In this example, we have cosecant -1 is equal to a negative square root of 2. Well, remember, guys, cosecant is 1 over y. That means sine is going to be y/1. So what you can do here is you can just rewrite this as a 1 over a negative square root of 2. Now, this might not seem make any sense to you. But again, if you rationalize the denominator, that's the same thing as a negative square root of 2 over 2. Now, again, when is sine negative? Sine is negative, negative square root of 2 over 2 over here and over here. We don't care about that angle. It's not within the restriction. This is the angle we're looking for. What coordinate point is when sine is equal to negative square root of 2 over 2? Well, that's going to be at a square root, that coordinate point here is square root of 2 over 2, comma, negative square root of 2 over 2. What coordinate point is that? What angle produces that point? And that angle, theta, is equal to a pi over 4. All right, so the last thing that we can kind of work on is also going to be when we have a composition. So here what we're going to be looking at is the composition of an angle, like a function of another trigonometric function. And all you simply want to do in this case is just kind of work from the back, like work from the inside out. All right. So in this case, in this example, I'm looking for the sine inverse of square root of 3 over 2. So again, I'm just going to say what angle what angle produces a y coordinate of square root of 3 over 2? Well, that's going to be a pi halves. So that's for the same thing. Pi over 3. So that's going to be the same thing as a cosine of pi over 3, which cosine pi over 3 is equal to a 1/2. So you can say this whole composition here is equal to a 1/2. I'm just kind of working it step by step. All right, what angle produces a negative square root of 3 over 2? Again, cosine negative, that's going to be in the second quadrant. Negative square root of 3, that's going to be a what? A 5 pi over 6. So then I can simplify this to a tangent of a 5 pi over 6. Now, 5 pi over 6 is going to be remember this coordinate point here is 1/2, comma, negative square root of 3 over 2. And the 2's will divide out, rationalize the denominator. That's going to be a negative square root of 3 over 2. So this answer is a negative square root of 3 over 2. And this answer, a lot of students like to do this. Don't do this, right? Don't just say the answer. It does not equal a 3 pi over 4. Don't do that. Don't do that, okay? Work through this inside out. Sine of 3 pi over 4 is what? The sine of 3 pi over 4 is going to equal to sine of 3 pi over 4. So 3 pi over 4, that 3 pi over 4, that's in the second quadrant, right? So that's going to be a square root of 2 over 2. So I have the sine inverse of the square root of 2 over 2. What angle produces a square root of 2 over 2? Yes, 3 pi over 4 does, right? But again, we have to follow that restriction. Remember, sine is restricted between the first and the fourth quadrant. So this answer, guys, is pi over 4, which is my original answer, which is pi over 4. So there, I'm sorry, guys. I forgot we had some trig or some word problems. I thought I was done. All right. So in this example, we are going to have to use our calculator. So this one says the height of a tower is 65 meters. Cast a shadow 35 meters along the ground. Find the angle of elevation from the ground to the top of the tower. Okay, so let's draw a picture. So we have the height of a tower. So let's just draw a tower. Okay, so that's going to be 65 meters. It casts a shadow. So there's going to be some sun here casting a shadow. Right? And that cast of that shadow is 35 meters along the ground. Okay, so from there to there, 35 meters. And then it says find the angle of elevation from the ground. So it looks like here's the ground, right? So angle of elevation, remember angle of elevation is going up to the top of the tower, which is right there. Okay, so basically, guys, we have a triangle. Here's theta. We have 65 and we have 35. Forget the units, whatever else, right? What are we trying to do? We're trying to find theta. Now, again, we have enough information, though, to write a trigonometric ratio, right? I can say the tangent of theta is equal to a 65 over a 35. So now I just need to use my calculator, right? And what I'm going to do is now I'm going to say theta equals a tangent inverse of 65 over 35. Make sure your calculator is in degree mode. And when you go ahead and type that in, you're now going to get a 61.699 degrees. And again, you can round or truncate however you need to. All right, so let's go and look at another one. Bearings. So this one says from city A to city B, a plane flies 6,500 miles at a bearing of 48 degrees. From city B to city C, the plane flies 8,100 miles at a bearing from 122 degrees. Find the distance and the bearing between city A and city C. Okay, so that's a lot going on. So it says from the city A to city B. Okay, so what I'm going to do is we have bearings. So I'm going to draw an XY axis. Okay, so what I always like to do is kind of start. Do I have room? I got a little room. Okay, so we have here's city A. Okay, now we're going to city A to B, 65 miles at a bearing of 48 degrees. So again, remember bearing starts at due north. So we're going to say 48 degrees. Okay, That's going to take us to B. Let's put B right here. Then it says from B to C, it flies 8,100 miles at a bearing of 122 degrees. So now what I'm going to do is I'm going to create another coordinate grid. And now I'm going to do 122 degrees. So 122 degrees is going to be probably somewhere down there. And that's going to take me to C. Okay, and then it says find the distance and bearing between city A and C. Great. So that's going to be here to here. Okay, so to find this bearing, what I'm looking for here is I'm looking for this distance and I'm looking for this bearing. Now, the cool thing is I already have 48 degrees, so I just need to figure out what that angle is. Okay, now this is kind of trouble if we don't have a right angle. So we better have a right angle here because otherwise we're going to be in kind of trouble. So if this is 22 degrees, then what does this angle have to be? Well, 22 plus what equals 180? That's going to be a 58, right? If this is 48 degrees, what does that tell you about this one, right? Because again, notice these are parallel lines. Yes. So notice how what I have here is I have what we call alternate interior angles, right? Remember that? So if there and there, did I have that? Did that right? Yeah. Or I did this one and that one. Yeah. Alternate interior angles. What am I doing? Jeez, come on. Right? So what I have here is basically this angle and that angle are equal to each other. So if that's 48 degrees, that means that is 48 degrees. And that, oh, I'm sorry. 48 degrees. No, that is not what I was looking at. If that was 48 degrees, that was not supposed to be 48 degrees. That was a mistake then. Because I was trying to make that to be a 32 degrees, which is incorrect. So I made a mistake there. I was actually doing this calculation wrong. So hold on a second. So we're going to change this. Sorry about that. I just noticed I made a mistake when I did this problem. Well, did the problem and created the problem. This needs to actually be a 32 degrees. Sorry about that. Because the reason being is exactly what I was just explaining to you. 48 degrees doesn't make sense. This has to be a 32 degrees. Because if that's 32 degrees, then that has to be 30 degrees. And again, like the reason why I know that we have to have that is we have to have a right angle. Because otherwise, at least what we've learned so far in this chapter, we don't have enough information. Okay? So that is going to be 32 degrees. Okay, the reason why this is, again, so important here, what we're looking for is let's kind of redraw this triangle. All right, and actually, let me go ahead and draw the sides here that we have. Find the distance between A and C. Okay, yeah, we don't have that. So we have, this is 6,500. Right, and then this was what? 8,100? Okay, so let's kind of go through the angles that what we have so far. So let's redraw this triangle. Okay, now again, 32 plus 58 is what? That's 90. Okay, so this one is 8,100. And then this side is 6,500. Okay, and then this angle, that's 90. So we're looking for this angle, which is going to be a theta. I want to figure out what that sliver is, that theta. Okay, because if I can figure out that theta, I just need to add it to 32 and I'm good. So first thing we need to do is do the Pythagorean theorem to find our D. Okay, so D is equal to, 6,500 plus 8,500 squared equals D squared. So that equals, say, 6,500 squared plus, say, 8,100 squared. Okay, so just go ahead and type that into your calculator and you should get D is equal to a 10,385.567 meters, depending on how you want to approximate that, which again, like makes sense, right? Because if that's 6,000 to 8,000, right? And that should be 10,000. Hypotenuse should be bigger. And we want to make sure everything's in meters, which is our final answer, right? Or miles, I'm sorry, miles. Okay, now to find this angle though, again, I need to look at this and say, all right, what information do I have? So I need to say tangent of theta is equal to an 8,100 all over a 6,500, right? So when I do that, and actually I got to calculate this. So that's going to be a tangent inverse of 8,100 divided by a 6500. Make sure you're in degree mode if you didn't already, because, yeah, okay. And that is going to give me a 51 degrees. Okay. Now, again, though, guys, that's not my bearing. My bearing is going to be theta plus 32 degrees. So the bearing is going to be a 0.25 degrees. So my bearing now is going to be a 51.25 degrees plus a 32 degrees, which is now going to give me a 83.25 degrees. That is going to be my bearing. So there you go, ladies and gentlemen. That is a little bit of word problems. We went through everything that I think if you have a trigonometry, test coming up, hopefully this was a excellent review for you. Hopefully you know a little bit more. You've built up some confidence. And if you have your test tomorrow or next week or coming up, I hope this review can be helpful for you. And otherwise, I have many more other videos coming up for you guys in trigonometry and in other topics. So I look forward to seeing you in another video. Cheers.